In our last set of videos, we looked at the first derivative and saw what that tells us about our graph, and now we're going to do the same thing with the second derivative. All right, so first we're going to look at this thing called concavity, and we'll see what that means. That's what I already said. All right, so recall the relationship between the second derivative of position, and that is acceleration. All right, so if we were looking at position, velocity, and acceleration, we've talked about second derivatives before. That just means you're taking the derivative of a derivative. All right, but if we were doing this with position, velocity, and acceleration, if we took the second derivative position, we'd get acceleration. So let's just say I have this graph. That is my position away from school or something like that. I'm driving my car. All right, so as I'm driving my car, I'm getting farther and farther away from school. What's going to happen to this position graph when acceleration is positive? So think about if you're turn the corner out of the front gate and you push the gas pedal, you're accelerating away from school. Well, when you first turn the corner, you're not really moving, so your position isn't really changing. But as you accelerate, your car's going faster and faster, so you're getting farther away from school at a quicker rate. All right, and your graph is going to look something like that. All right, so if this is when you're leaving the front gate, you're making that right-hand turn out of the front gate. You start off really slow. All right, your position is not changing much, but as you push your foot on the gas pedal, you start going faster and faster, so your position away from campus is changing quicker and quicker. All right, so this is what it's going to look like when you have a positive acceleration. What's it going to look like when your acceleration is negative? All right, let's think about an example. Let's say you're traveling along Foxcroft Road and you have to slow down because there's a deer in the road. All right, so as I'm traveling along, I'm getting closer to school. All right, I'm traveling at this kind of constant rate. Actually, make it a little steeper. All right, so I'm traveling along at this constant rate. I'm getting closer and closer to school. And then I see this deer in the distance. So as I slow down, as the deer is getting closer, my position's not going to change as much. And then maybe I even stop, so my position doesn't change at all for some amount of time. And then maybe I can speed up and get closer to school. All right, but as my car slows down, you can see this kind of curve happens in the graph. All right, so you can see as I'm accelerating or slowing down, all right, it's going to cause these curves in my original graph. And the curve, this kind of curve shape, is known as the concavity. And if you've, in physics class, you've talked about mirrors, you kind of have two different types of mirrors. You can have concave and convex mirrors. All right, it's just how the mirror is curved. Same thing for this. Our second derivative tells us how our graph is curved. All right, and a bigger second derivative, the more the graph's going to be curved. If you have a small second derivative, it's going to be barely curved like that. All right, so when the second derivative is positive, we say the graph is concave up. And the way to remember kind of what that looks like, it's concave up like a cup. All right, so you draw a cup, and that is a concave up graph. All right, also kind of looks like a smile. All right, so second derivative is positive, concave up like a cup. When the second derivative is negative, the graph is concave down like a frown. So if I just draw a sad face, all right, that is a concave down function. All right, so concave up like a cup, positive, concave down like a frown is when it's negative. All right, when the second derivative changes sign, we call it an inflection point. So that could look something like this. Actually, just draw the whole cup to the whole frown. All right, so when I have this kind of switch in my concavity, that's an inflection point. It can happen the other way as well. So frown to cup, this would also be an inflection point. All right, so here's the kind of curve of your function is changing. It's called an inflection point. All right, so f of x equals x cubed minus 6x squared minus 7. All right, all the intervals where the graph of f is concave down. So we're looking at concavity. We're talking about the second derivative. And then we're just looking at positive or negative. So again, we're going to have to make a number line and look at our positive and negative values. But still, the first thing we have to do is take the second derivative. So 3x squared minus 12x. Take the derivative again, 6x minus 12. And again, to do these things we're comparing positive and negative, we start by setting it equal to 0. And we get just 2. All right, so there's one important value that happens at 2. we do our test points, so 0 to the left, anything to the right, let's just say it would be like 4. If I plug in 0 into my second derivative, because I'm talking about concavity, so I want to plug into my second derivative, I'm going to get negative 12, so I get negative values there. If I plug in 4, 4 times 6 is 24, minus 12 is 12, so that's positive. Everything else is there is positive. All right, so when is my function concave down? When the second derivative is negative, which happens from negative infinity up to 2. All right, this whole part of my number line. All right, so these number lines are important when you're talking about the first derivative and the second derivative.